Okay, hi class. This is part 2 of chapter 2. So remember, I didn't record the lecture last week, so I just posted part 1 to YouTube. This is going to be part 2. So part 2 is about different kinds of models. So in the previous lecture, remember we had a tank model. We had water coming out, water going in, okay, and then we had as a state variable the height of water in the tank. Now this height is a continuous variable. It is not discrete. It changes continuously, and so because of that, we could model this system using a differential equation, right? Because differential equations are good at modeling continuous variables. So we had, I think for this one, we had what, Q1 minus K1 H over A. That was our model for this system. And the other thing about it was, which probably may have not noticed, is that the system is also deterministic, meaning if you solve this, if you were to run a simulation, for example, of this model, every time you run the simulation, you get the same answer. So there's no stochasticity in the model. So this, what we say, this model is a continuous deterministic model. These are very common kinds of models. A lot of electrical circuit models are continuous deterministic. A lot of mechanical models are continuous deterministic. A lot of chemical models, like chemical reaction networks and so on, as long as the concentrations are high enough, are also modeled as continuous deterministic models. So it's a very common way to do models. But there are other ways of building models, and the second half of chapter 2 talks about this. And it talks about there's two other ways that we can talk about these kinds of models. First of all is it's discrete. So the opposite to continuous will be discrete. And the opposite to deterministic is stochastic. Okay. Now the kinds of, and you can have combinations of these. So I could have a continuous stochastic, or I could have a discrete deterministic, and so on. So there's actually 4 combinations here. And a discrete model is one where the state variable jumps in discrete values. So an example of a discrete model might be the spread of an infection. So spread of an infection in a small population. So let's say you had 50 people you were modeling. 50, they're individuals. You've got the number of people that are infected will be a discrete number. 30 might be infected, 32 might be infected. You don't get 31.5 people infected. So this is best model as a discrete, using a discrete model. Okay. I won't go into the mathematical form that you would represent this as a discrete model, but you can have discrete models. The other thing about this infection model, of course, the chance of, if this is a common cold, the chance of catching an infection is probably quite stochastic. So this would also be a stochastic model. Okay, now stochastic model is one where if you ran the model multiple times, each time you run it, you get a slightly different answer, right? Because the chance of getting an infection, of passing the common cold onto someone else, is quite random. So this would be modeled as a discrete stochastic system. What other systems we have? If you have a large population, you might model that as a continuous stochastic system, and so on. So there are various combinations of these that you can model. In this class, we're pretty much only concerned with continuous deterministic models. Okay. Now, given a deterministic model, you can also classify models into various ways. So let's look at that. Classification, okay, of models. The big one, I guess, is linear or non-linear. Now we'll talk a lot more about this next week. But in simple terms, if your variables, your state variables, aren't raised to any power greater than 1, for example, then you can class it as linear. Otherwise, it's non-linear. We will pretty much exclusively be looking at linear systems because those are the most well understood. The other kind of model is whether it's time invariant. Time invariant. That basically means whether the model itself is a function of time explicitly. These aren't that common, I don't think, and we certainly won't be looking at them. All our models are time invariant, i.e. there isn't an explicit t time variable on the right hand side of the differential equation. So if I have a differential equation, say I had dh by dt and it was some function of time, so it's a function of the height, some parameters, some inputs, and time, then that would be a time variant system. Okay, but we don't have time on the right hand side, so it's time invariant, and these are the only ones we will be considering. Okay, now in practical terms, what that sort of means is, it doesn't matter when I start my time clock in t, I'll get the same results every time. So it doesn't matter whether I run my simulation in the morning or the afternoon, I pretty much get the same answer. And the other classification is related to whether the models are dynamic or static. All the models we will be dealing with are dynamic, i.e. they change in time. A static model might be something like a resistor network, right, with no capacitance at all, just resistors. And then you can assume that there's no when you turn, let's say you connect a battery up to a resistor network, we often assume that the changes in voltages at all the nodes are instantaneous and there's no change after that. Okay, so that might be a static model. There are a couple other divisions. What have we got here? I mean, there's what they call lumped models. Lumped models, or distributed models. What have I got this here? Maybe I don't include that anymore. Okay. Yeah, I don't include that anymore. So let me get rid of that. Basically, it's to do with the granularity of your model. You either create a model in great detail, try to include everything, or you build a model using sort of simplifications. For example, if you're modeling a transistor, you could model it just as a simple function of a simple nonlinear function of the current input. But you could also model it by delving into the solid state physics of the NPN junction or the PNPN junction. So there are different levels at which you can model. We won't concern ourselves so much to that, but it's very important for complex systems where you can't really model it in fine detail and you have to use higher levels of descriptions when you build the models. Okay, I think that was it. I don't think there was anything else I wanted to say. Let me check. I think that was it, yeah. Yeah, so those are the basic classifications of models and the idea of continuous, deterministic, and discrete and stochastic. You make these decisions based on a case-by-case basis. When you come across a problem, you decide, should this be a continuous model? Should this be a deterministic model? Should it be a stochastic model or a discrete model? And then when you build a model, you may discover that it's a linear, time-invariant, dynamic model. And the classification will affect how you perhaps solve the problem, but we won't delve into that too much. Okay, that's it for now.